Continuing our discussion on kinetics, this is the second video on reaction mechanisms. As a reminder, reactions may require more than one step. A reaction step is called an elementary reaction. Reaction mechanisms, which are the aggregate of the elementary reactions, are proposed and then tested for validity and then for actuality. Two requirements must be met for a reaction mechanism to be valid. The first is the sum of the elementary reactions must add up to the overall reaction, and the second is the proposed differential rate law, which is derived from the reaction mechanism. Second, the proposed differential rate law derived from the reaction mechanism must be identical to the experimentally determined rate law. In the previous video, we worked on requirement 1. On this video, we'll be looking at requirement 2. Quick review again. For an elementary reaction, the rate law for that step is related to stoichiometry. If this is an elementary step, the rate law is the concentration of the reactant raised to the power of its coefficient. So this rate law would be a rate equals reaction constant times the concentration of A squared times the concentration of B. If this were an elementary step, the rate law would be K times the concentration of AB times the concentration of C. Now, the speed of a reaction can be no faster than the slowest step of that reaction mechanism. As an analogy, imagine you're driving a sports car up a hill at 160 kilometers per hour. You go 160 kilometers per hour until you get behind a logging truck, which is going 60 kilometers per hour. You no longer can travel at 160 kilometers per hour. You can only go 60 kilometers per hour. The speed of a reaction can be no faster than the slowest step of that must be equal to the overall rate law. Now, in a multi-step reaction mechanism, there are two possibilities. The first step is the slow step, or the first step is not the slow step. Let's go with the first step is the slow step. We use this generic reaction, and then experimentally we determine that the rate law is rate equals K times the concentration of A sub 2. This is the proposed mechanism. The first step is the slow step, the other two are fast. We cross out the intermediates, add up what remains, and we see we get the overall reaction, so requirement 1 has been met. Now we look at the rate laws. The slow step rate law is K equals A sub 2. The slow step has this rate. This is the rate law for the first fast step. This is the rate law for the second fast step. The slow rate is the rate limiting or the rate determining rate law. We see that it is identical to the experimental rate law. This is a valid potential mechanism. Let's take the same equation, but now the experimental rate law is K equals the concentration of A sub 2 B sub 2. The same reaction mechanism is proposed. So once again, you cross out the intermediates, add up what isn't crossed out, and you get the correct overall reaction. The rate laws are like they were before. The slow rate sets the overall rate. You compare the slow step rate law to the experimentally determined rate law, and you see that they are not identical. That makes this an invalid mechanism. Now, what if the first step is not the slow step? Here is our equation again. We'll use the same rate law that we used for the last example. We know that the previous reaction mechanism was invalid, so a new reaction mechanism is proposed. This is what that reaction mechanism looks like, where the first step is the fast step and the second step is the slow step. You get rid of the intermediates, and when you add up what remains, you get the correct overall reaction. Requirement 1 is met. Now we look at the rate laws. The fast rate law is rate equals K times the concentration of A sub 2 times the concentration of B sub 2. The slow step, the rate equals the concentration of A sub 2, B sub 2. This is the slow rate. We compare it to the experimentally determined rate law, and the elementary rate law is not the same as the experimental rate law, or is it? When the first step is not the slow step, then the step before the slow step goes into what is called equilibrium. In chemistry, equilibrium means that the rate of the forward reaction, in this case, A sub 2 plus B sub 2 becomes A2B2, is equal to the rate of the reverse reaction. A sub 2, B sub 2 becomes A sub 2 plus B sub 2. So you look at the rate law for the forward reaction, and it has to equal the rate law for the reverse reaction. Divide both sides by the reverse reaction's rate law constant, and you get an entity that looks like this. The rate law for the slow step is K times the concentration of A sub 2 B sub 2. But we just showed that this entity equals this entity, so we are going to, so you end up with this. But a constant times a constant divided by a constant, as you see here, is still a constant, so this simplifies to this. So now we can say that the rate equals K times the concentration of A sub 2 B sub 2 equals the rate constant times the concentration of A sub 2 B sub 2, which is the experimentally derived rate law. So in actuality, the rate laws are the same, and this is now a valid mechanism. Now, of note is the fact that intermediates are rarely in the final rate law. So if your rate law contains an intermediate, you have to take a close look at it. But rarely doesn't mean never. So occasionally they are included, and the College Board at times has asked questions where an intermediate had to be in the rate law. So here is a problem for you to attempt. Is this a valid potential mechanism? Run through the steps, get your answer, come back and check it. Go. We need to figure out if condition 1 is met and if condition 2 is met. Let's look at condition 1 first. We write out the equations, we eliminate the intermediates, and then add it up, and we can say that we do meet the condition 1 requirements. So now we look at the second requirement. We know that this is the rate law. So we set things up. The first rate law for the fast step looks like this. For the slow step, it looks like this. So we take the rate law before the slow step, and that will go into equilibrium. The forward rate has to equal the reverse rate, so the rate law going forward has to equal the rate law going backwards. Divide both sides by the rate law for the reverse reaction. Now we can substitute that into the rate law equation for the slow step. You get rate equals a constant. That looks like this. We're going to simplify things. The constants become one constant. The nitrogen monoxides, there are two of them, so you can square it, and you get rate equals a rate constant times the concentration of nitrogen monoxide squared times the concentration of chlorine. This matches the experimental rate law, so we have met the requirements for condition 2. Therefore, we can answer the question, is this a valid potential mechanism, with a simple word, yes. So to review, reactions can proceed in a stepwise manner, even if there's only one step. Each step is called an elementary step or an elementary reaction. The rate law for an elementary step is derived from the stoichiometry of that step. Rate equals K times the concentration of the reactant raised to its coefficient. You have to meet two conditions for a valid mechanism. You must get the overall reaction when the steps are added together. The rate law for the slow elementary step must equal the experimental rate law. The slow step sets the overall reaction rate. If the first step is the slow step, then that rate law must look like the experimental rate law. If the first step is not a slow step, you may need to do some algebraic manipulation to compare rates. And that concludes our videos on reaction mechanisms. There will be further kinetic videos.